Now we should turn to a concrete example, and then we will see that this is not as complicated as it might be suggested by these very abstract definitions. And for this, we are just going to look at a two-level system. So a system with a state given of this form. And first have a look at what this means in this case, that we just have this single state, so that we are dealing with a pure state. And I'm going to do it in our two different languages, using the Dirac notation and our notation of vectors, where we will see how simple it actually will be. So first of all, in terms of the Dirac notation, the quantum state is defined in the following way. So this is a pure state, and then we just insert the definitions here. Now here we just have our normal quantum state, alpha 0 plus beta 1. So this covers this part here. And then we have the dual state. For this we then have this complex conjugation of the coefficients. And now we can multiply out all terms. And get this following result, which I've written. I've ordered everything so that we have really the placeholders for the different elements of a matrix. The entry is 0, 0, 0, 1, 1, 0, and 1, 1, so that we can directly translate this into the corresponding matrix. And when we do this, we see that this corresponds indeed to the following product of a vector with the Hermitian conjugate, very similar to what we have in the scalar product, but in the opposite order, just as here where we don't have the scalar product, but the states multiplied in the opposite order. So this covers the case of a pure state for this two-level system. Now for a mixed state, ρ is a sum of such states, but each of these just looks like a density matrix of a pure state, just as defined here. So we will simply have to sum up matrices of the form given as here. And what we will then end up is with a Hermitian matrix. So we can always write this in terms of the elementary Hermitian matrices that we have encountered before, the identity matrix and the three Pauli matrices. So let me write this in this form, where all the coefficients A, B, C, and D are real numbers. Now we can work out the expectation values for the corresponding four different observables. And we will get a very simple result in each case. For the identity matrix, we simply obtain the trace of I times ρ, and the identity matrix just does not change anything, so we will get the trace of ρ. Now if we look at the matrices that we have here, and we look at the explicit forms of the matrices x, y, and z, then the trace all vanishes. The Z matrix has entries 1 and -1 on the diagonal, so if you add them up you get 0, and the other two matrices just have zeros on the diagonal, so the sum of the diagonals is certainly 0 as well in this case. So if we now calculate the trace of ρ, then the only place at which something can be picked up is here, and this is a 2 by 2 identity matrix, so its trace is actually 2. So what we then obtain is 2 times A. Now what we want to have here at this point is of course 1, because this is our normalization condition. So we conclude that for any density matrix of a two-level system, the coefficient A must always be 1/2. And this is simply our normalization condition. Now when we next calculate the expectation value for the observable x, then we have to calculate the trace of this 2 by 2 matrix. So we have to multiply each of these terms by x. Now if we multiply the identity matrix by x, we simply obtain x, and the trace of this matrix vanishes, so this does not give us any contribution. So we don't obtain any contribution from this term. And similarly, when we multiply y or z by the Pauli X matrix, we simply obtain one of the other Pauli matrices, and again the trace of these Pauli matrices vanishes, so we don't get anything. But if we multiply x by itself, we obtain the identity matrix. So x squared is the identity matrix, and the trace of this is again 2, so the result that we obtain is 2b. And now analogous, you can see that the result for these expectation values here is 2c and 2d. Now when we first encountered these expectation values for a two-level system, we grouped them into a vector, the so-called polarization vector, which is also denoted by a symbol p. So we have these entries px, py, and pz, all grouped into a vector p, where I always place this arrow symbol on top so that we make sure that we know that this is the polarization vector. So now we can simply rewrite everything in terms of this polarization vector, and our most general form will be the following. And we often also denote it by the following shorthand notation. So we have here some kind of dot product between these entries px and the Pauli matrices. Now this is just a formal definition of this dot product, and we actually already encountered it once when we looked at the unitary time evolution operator of these two-level systems. Now for a pure system, the polarization vector was of unit length, but we now see that for a mixed state this is no longer the case. Indeed, when we look at a maximally mixed state for this two-level system here, the Hilbert space dimension is 1/2, so ρ would just be 1/2 times the identity matrix, and this corresponds to the case where the polarization vector vanishes. And indeed there is a very simple relation between the length of this polarization vector and the purity of the system. And we obtain this by simply writing down this form of the density matrix explicitly as a 2 by 2 matrix. So I write ρ here. Now we have the identity matrix multiplied by 1/2, so we get diagonal elements of 1/2 on the diagonal from this contribution. And then the other diagonal matrix is the Z matrix, and there we get plus or minus pz. And then we have the X matrix and the Y matrix with off-diagonal elements, and they simply combine to give us these off-diagonal matrix elements. And from this we can then calculate the purity simply by matrix multiplication. And the result that we obtain is of the following form. Which we can simply write in terms of the length of the polarization vector as given here. Now you can actually obtain the very same result by just starting from this form here and work out first the square of this density matrix given with these matrices. What you will then encounter are products of Pauli matrices and products of Pauli matrices with the identity matrix. And so this is just going to reduce into other Pauli matrices and the identity matrix. And just as before, the only contributions arise when the identity matrix is multiplied by itself, or any of the Pauli matrices is multiplied by itself. So this gives you a quarter, px quarters, py quarters, and pz quarters, multiplied by the trace of the identity matrix, which is just 2, and at the end you will just get the same result as given here. This will indeed be a very nice feature of many of the calculations that we do later on in this course, that we can do them in different ways, and can always find a way in which they become particularly simple or just according to our preferred taste. Just as here, because when you think what this really means in practice is we are just multiplying 2 by 2 matrices and adding up elements of these matrices, say along the diagonal. So these are very simple mathematical operations. And in practice, our calculations will not be more complicated than this. The most complicated thing that we will encounter in these calculations are simply 4 by 4 matrices, which are simply related to the composition of 2 two-level systems into one larger composed system. So let us have a look how the density matrix indeed looks like for 2 such composed quantum systems.